Hello everyone, welcome back to the Fractal Frontier Maths. In the previous video, we explored the comparison theorem in differential equations and learned how to use it effectively to determine the maximal interval of existence for solution of an initial value problem. We have discussed a problem from CSIR NET June 2017 in which we determine the existence interval of this initial value problem using comparison theorem. We also saw how comparing with simpler differential equation help us to predict blow-up behavior and boundedness of solutions. So we have discussed here the comparison theorem. If y dash x equal to fxy and u dash x equal to g of u with fxy greater than equal to zy and y0 equal to u0, then yx is greater than equal to ux for all x in the common interval. In today's video, we are going to apply those concepts to a very interesting problem from CSIR NET December 2019 involving the equation dy by dx equal to x square plus y square, which is the same differential equation as in the previous video, and the condition is just changed y0 equal to 1. We will carefully analyze statements related to existence, uniqueness and boundedness and singularity formation. We will use the comparison theorem to determine where the solution stays finite and where it must blow up. We will also examine why the solution remain bounded on certain intervals and become unbounded or others. After that, we will look at another additional problem from the CSIR NET December 2019 paper to strengthen our understanding on the comparison theorem and its result. Before discussing the solution, you are all advised to check the previous lectures so that you can better tune in to today's problem. Also, in the end, we will provide a general result for such kind of differential equations. Let's begin. So the initial value problem is given as dy by dx equal to y square plus x square subject to the condition y0 equal to 1. Let's assume that fxy equal to y square plus x square, which is a continuous function because it's a polynomial function. So this is the comparison theorem. If y dash x equal to fxy and u dash x equal to gu with this condition for all x, then yx greater than equal to ux. So we will use this comparison theorem. For more detail, check out the previous video. Here fxy equal to x square plus y square, which is greater than equal to y square. For all x greater than equal to 0, we will consider the differential equation du by dx equal to u square. So here g of u is u square and the condition is the same as the initial value problem given in the question. Y0 equal to 1, we have taken u0 equal to 1. Now we will solve this equation and decide the blow-up behavior of the solution yx. Since here x square plus y square is fxy, so fxy is greater than equal to g of y, where g of u is assumed as u square. Now consider the differential equation du by dx equal to u square. By using the method of separation of variable, we will arrive at minus 1 upon u equal to x plus c, where c is constant of integration. The condition is u0 equal to 1. By using that condition, we will get c equal to minus 1. So the solution is ux equal to 1 upon 1 minus x. So the solution blow up at x equal to 1. So the maximal interval for du by dx equal to u square subject to the condition u0 equal to 1 is 0 to 1, where 1 is not included. And by comparison theorem, yx greater than equal to ux and ux tends to infinity as x tends to 1. Therefore yx cannot exist past 1. Therefore we can conclude that since the function f of xy equal to x square plus y square is a Lipschitz function, so there exists a unique solution, okay, about x equal to 0. So there exists a unique solution is a correct option. As we know, every solution is bounded in 0 to pi by 4. Since we have that the solution blow up past 1, therefore before 1 in interval 0 to 1 the solution will remain bounded. So the solution yx will be bounded in 0 to pi by 4, which is a part of the interval 0 to 1. So the first option is correct, second option is correct, and the third option is the solution exhibits a singularity at some point in 0 to 1. This is also correct because it blow ups at 1, at least 1 or after, so it has singularity in the interval 0 to 1. So this is also a correct option. Third option, last option is the solution becomes unbounded in some subinterval of pi by 4 to 1, which is also true because this interval is a part of close 0 open 1. So this option is also true. Hence for this problem, which is asked in CSIR NET December 2019 paper, all the 4 options are correct options. Let's discuss another problem from CSIR NET December 2009, which is a second paper held for Assam. So the problem is, let mod fx is less than equal to 4 mod x for x belongs to R, the largest possible value for mod x1 where x dash t equal to f of xt for t greater than 0 and the condition is x0 equal to 3. So we have to find the largest possible value of x1. So to use comparison theorem, we assume the function g of u as 4u. So we consider the initial value problem, du by dt equal to 4u subject to the condition u0 equal to 3. Now we solve it by using the method of separation of variables. We will get the solution log u equal to 4t plus a constant log c. To determine the constant, we will use the condition u0 equal to 3 and we will arrive at c is equal to 3. So the solution will be ut equal to 3 exponential 4t. So by the comparison theorem, xt will be less than equal to u of t. So xt will be less than 3 e raised to the power 4t. We have to find the value of mod x1. So x1 here will be 3 e raised to the power 4. So the maximum possible value for mod x1 is 3 e raised to the power 4. Hence the first option is correct. We can also approach this problem by using Gronwall's inequality. So this is the statement for Gronwall's inequality. If u dash t is less than equal to beta t u of t for t belongs to some interval I, then ut is less than equal to ua exponential integral a to t beta s ds. So in our case, we take ut as mod of xt and a equal to 0. So then by the Gronwall's inequality, ut means xt t mod less than equal to u0 exponential integral 0 to t. Here beta is 4 because we are given that mod fx is less than equal to 4 mod x. So ut will be mod x and beta is 4. So by solving it, we get mod xt is less than 3 exponential 4t. We have to find the value of x1, so mod x1 is less than equal to 3 exponential 4. Hence first option is correct option. We can derive a general result for the initial value problem. Dy by dx equal to x square plus y square subject to the condition y0 equal to y0. The largest interval of existence for this initial value problem will be 0 to 1 by y0. So by using this general result, we can solve multiple problems in lesser time. So this is an important result. You can derive it by using the comparison theorem. So this is it for today. In next video, we will discuss some other problems on the topic existence and uniqueness or interval of existence. So make sure to watch all the previous video so that you can get the next video very easily, because all the videos are connected. We will discuss the concept of initial value problems by using the problems asked in CSIR NET exams, and we build step by step process to solve the problems.